May I know if the recording has been started? Okay, thank you. So, good afternoon, everybody, and welcome back to this session on climate data science. So, today we will be again going through the similar. Okay, sorry. We'll be going through the similar pattern in which the first half we will go through the some theory, and then I will start with the TensorFlow basics today, which is very important, and we'll try to see how much we can complete. And it is based on the official TensorFlow, uh, like the material, the tutorials that are available on the TensorFlow website. So I also have pulled the material for PyTorch. Uh, let us see how much we are able to do in today's session. Otherwise, we will be carrying it forward in the next further classes as well. So in this class, we will be starting with the. So there is. I was talking about the deep learning specialization. We'll be going through the material of deep learning specialization in this class. And so this is a course on Coursera. It's one of the fundamental resources to learn data science or machine learning. So this course this is a summary prepared by someone who actually has done this course, and you can see that. Okay, so this is a specialization offered by deeplearning.ai, and if you go and see the deep learning specialization, so this specialization has got 5 courses: neural networks and deep learning, improving deep neural networks, hyperparameter tuning, regularization and optimization, structuring machine learning projects, convolution neural networks, and sequence models. So the first 3 courses are on the basics of neural networks and machine learning, whereas the fourth course is dedicated to the computer vision problems using convolution neural networks. And the last course is on sequence models. So sequence models, we mean the models which are used to uh, which are or used or developed over data sets which have a temporal relationships. So that's about the a summary of these courses from deep learning specialization. So yeah, just give me a minute. I'll be back. Okay, so sorry for the interruption. And in this specialization, so we will be covering this on a fast forward mode. And basically this each readme is prepared for each of the course. Typically, if you do these courses on a like on a fast forward way, you can take from 1 week to 1 month to up to 3 months per course. So that depends upon what you're doing. So we will cover the basics. And so he says that if you want to break into cutting edge AI, this course will help you to do so. And deep learning engineers are highly sought after these days, and mastering deep learning can give you numerous career opportunities. So I think for our case, we are more interested into applications of AI in climate data science or in climate data. And so the entire space of AI is being powered by deep learning. And so Andrew, so this course is also, I think I did not talk about the guy who is behind this course. His name is Andrew NG. For those of you who don't know, Andrew NG is the one who started the course Machine Learning on Coursera. He is the founder of Coursera as well. And this course is like the is a very fundamental course on understanding the basics of machine learning, and it has been taken by more than 5 million learners worldwide. And this course first came out in somewhere around 2014, and it is basically on Octave, which is which is a which is similar to MATLAB. And so feel free to go through this course, and I would highly recommend it. And so they also have subtitles in different languages. So he was like the first one of the first persons who basically motivated a lot of young people to take up machine learning, including me. And and after that, in 2018, 2019, so he launched a company. It's called deeplearning.ai. And deeplearning.ai is basically hosting courses on Coursera. So yeah, so these are all what Andrew says. It says that deep learning is the new superpower that will let you build AI systems that just weren't possible a few years ago. So we'll see why he's saying that and what does he mean by that. And so when once you finish this class, so this will finish in this session itself. So we'll understand the major technology trends driving deep learning, be able to train, build, and apply fully connected deep neural networks, and know how to implement efficient or vectorized neural networks and understand the key parameters in neural networks architecture. So what is a neural network? So as we have seen in brief in the previous classes, a neural network consists of neurons, or which we call as the nodes of our network, and a single neuron without any nonlinear activation or is equal to linear regression. So linear regression is the most simplistic neural network, and a single neuron will basically, what it will do is it will compute a weighted sum of the input. So for example, if you remember from your linear statistics class, if you when you're trying to fit a linear equation over some data points, you would basically do y is equal to mx plus c. So this is what is being attempted in a neural network as well. So a single neuron will compute a weighted sum of the input, where are the weights, w transpose into x, and you can add a bias term or a constant as well to this. And then he says that we can set a threshold to predict output in a perceptron. If the weighted sum of input crosses the threshold, perceptron fires, and if not, perceptron doesn't predict. So we basically compute this operation. So this is a linear combination of the inputs based on different weights, and then we apply a nonlinear activation function to it. And that nonlinear activation function, it decides whether the perceptron will what will our perceptron do. And it can take both perceptron can take both real or boolean values. So by the way, perceptron is basically what we so what is used most popularly, it's in the terminology of multi-layer perceptron. You would have read the term MLP. And a multi-layer perceptron, typically people talk about when they will say MLP, it's a three layer neural network with an input layer, a hidden layer, and an output layer. And all these circles, these are the neurons. So the inspiration is from biological neurons in the human brain, and the arrows here correspond to the weights. Okay, so it's just like y is equal to mx plus c. M and c are our weights. X is the independent variable, y is the dependent variable. Now once you compute the linear combination of the input, you would typically apply a nonlinear activation function, which would complete the operation, and you will get the value of the hidden layer. And the weights that you are trying to uh, it's the weights that you're trying to basically find out what is the value of those weights. And we basically compute some kind of a function also known as loss function, which is minimized to generate optimum set of weights. And so he says that when wx plus b or y is equal to, you can say mx plus c or wx plus b is equal to 0, the perceptron would output 0. So you can so think of as, so the linear combination, if it is 0, then it will output as 0. And if you we'll see the different nonlinear functions, and you'll understand how this statement is true. Now, the disadvantage of perceptron is that it only outputs binary values, and if we try to give a small change in the weight and bias, the perceptron can flip the output. So basically, so yeah, here he's talking about uh, basically talking about something in terms of a classification problem. And it would, so for a class, for particularly for binary classification problem, you would typically output only two values. So he's saying you would output only binary values, and we need a system which can modify the output slightly according to change in the weights and bias. So here then comes the sigmoid function in practice. So what is sigmoid? As we discussed in the previous classes, it is just 1 upon 1 plus e to the power of minus x. It is one of the earliest, most popular nonlinear activation function. And it basically, what it would do is, uh, it is a system which can modify the output slightly. So if you make a slight change in the weights and biases, it would change your output, not drastically. And if we change the perceptron with a sigmoid function, so we can change the output. And so he says that if you apply a sigmoid activation function, then a single neuron will act as a logistic regression. So when we are talking of classification problem, and we are using a very simple, so it's just like we have linear regression for if you are trying to predict the exact values, we have something called as logistic regression for classification problems. If you are trying to classify, let's say, from images, whether the image belongs to a cat or a dog, or in our case, whether this is a drought or this is a flood or this is a mesoscale convective system. And so he says that we can understand the difference between perceptron and sigmoid function by taking a look at sigmoid function graph. So the simplest neural network graph, it looks like this, as we already discussed: an input, a hidden layer, and an output. And uh, an activation function which started becoming popular since 2019 2020 is known as ReLU. So ReLU stands for Rectified Linear Unit. Now this rectified linear unit, so just like sigmoid is 1 upon 1 plus e to the power of minus x, ReLU is max of 0 comma x. So you basically filter out all the negative values, and if the number is greater than 0, so it will just pick that number. Otherwise it will assign, so for all the numbers which are 0 and less than 0, it will assign them as 0. And it is the most popular nonlinear activation function right now that makes deep neural networks train faster. So sigmoid was slower, ReLU is faster. And hidden layers, they predict the connection between inputs automatically, and that is what deep learning is good at. Now you have to understand that how people would typically do AI before the advent of deep learning. For example, if we talk about the image classification problem, they would basically make features, manual features. For example, how the ear looks like, how the eyes are, how the nose is. So they would manually create those kind of features and then input it to some kind of a simplistic model to do the predictions. Now, what deep learning did for us is that it the deep layers, or so as we see, if you have the number of layers greater than 3, including the input and output layer, it's a deep neural network. And what the hidden layers are doing for you is they are trying to identify the connections between the input and output, or trying to identify the mapping from the input and output in an automated way. So what do we mean by automated way is basically it is we are trying to optimize the weights and minimize the loss function. In that process, the weights are getting tuned automatically. So deep neural network consists of more hidden layers, and each input will be connected to the hidden layer, and the neural network will decide the connections. So you give the data to the model, and so this is my model. For example, you can and this is the so this is the what we call it as the architecture of the model. And so this in this case you can decide on the architecture, you can tune the architecture as well, and it is your model which will decide what would be the values of the weights that would correspond to the best fit to the label data set. In this case, label data set, but we can use deep learning also for unsupervised learning problems. Now, supervised learning means that we have the X and Y pairs. So what do we mean by X and Y pairs is that we have an X, we know what is the input, we know what is the target. So we have that data set, the labeled data set, as something which is given to us or we prepare, and we are basically trying to create a function which maps from X to Y. So doing supervised learning with neural networks, you can have different types of neural networks for supervised learning. So first is the convolution neural networks, or CNNs, which are useful in computer vision. So CNNs would basically operate on the 2D images. Then we have something known as the RNNs, or the recurrent neural networks, which are very useful in speech recognition or natural language processing, and also these are used for time series forecasting. Another type of neural network is standard neural network, or which is useful for structured data, let's say some kind of tabular data. And then you can basically create your custom or hybrid neural network architecture, or a collection of different neural networks. And structured data is something which is like the databases or the tables. It is having a proper structure. You have, for example, the variable names, you have a common length of the data set, and it's all it can be stored in a proper structured database. And unstructured data is like images, video, audio, text. And structured data gives more money because, yeah, so he says that companies rely on prediction on its big data. So we have to understand that what these guys mean by what the kind of big data that they are talking about is actually very small as compared to the big data that we talk in the climate science community, because our data sets are like, for example, the global data set that would span the entire globe, and if it is a three-dimensional data set along the levels, and then also in the time dimension. So if you are storing it at very high temporal frequency, then your data set is going to be huge. So why is deep learning taking off now? Deep learning, he says, is taking off because of primarily because of three reasons. One is the data. So you can see, as you can see from this plot, that as you increase the amount of data in any model, so for example, in a large neural network, medium neural network, in a traditional neural network or logistic regression, your performance is typically increasing. But if you keep on increasing the size of your neural network, then also your performance is increasing. Also, we basically have lots of data sets today. Now in the business world, they have big data collected on mobiles, on IoT devices. We have satellite data sets, ground-based observations, model simulations, and different geophysical data sets pertaining to different use cases. And for big data, a big neural network is better than a medium neural network, which is better than a small neural network. And neural networks have shown to outperform linear regression and support vector machines. So support vector machines used to be the state of the art before neural networks came into the picture. And so this is the data is the first reason why deep learning is taking off. The second reason is computation. Now we have the access to high-end GPUs, we have powerful CPUs, accessibility to distributed computing over so you can run or train your models across the different CPUs and GPUs or a combination of both. And you can also have application specific integrated circuits. So these days a lot of new processing units are coming. For example, Google has launched its own TPU. So TPU is Tensor Processing Unit. Now Tensor Processing Unit would typically have, so it has the neural network embedded on the chip. So that would basically make your computation even faster as compared to the GPU. And the TPU is, so they're not selling it in the market. So you can only rent it on the cloud. Then you should also, so there was a very interesting workshop, or I would say, so Tesla recently organized this thing. It's called the Tesla AI Day. And in Tesla AI Day, they basically announced a new chip. So this happened on August 2021. And they announced a new chip. It's called the DPU. DPU is basically Doge Processing Unit. And yeah, I will just show you that. So Doge processing unit is, so they are planning to use, it's an in-house thing, in-house chip which they have developed at Tesla. And they are planning to use it for self-driving cars. And they have reduced the different bottlenecks like bandwidth and communication. And so this is an example of ASIC, application specific integrated circuit. We can, so they would perform large scale deep learning on this, on the DPU. And it is not available to the public as of today. So you can see that they are having, so these are the small chips. They are combining these chips, and they're creating this is the final uh, product that they have. And this is a very recent example of a new new hardware, which is, so hardware, we have to understand, is the thing which is driving the entire progress or the ecosystem of AI and ML. Because the papers or the conceptual understanding of neural networks that was there even in 1980s and 1990s. What we were lacking was good quality of data. So data, but still can be collected, but we did not have the kind of GPUs and TPUs and DPUs that exist today. Now, the third thing is which is driving deep learning are the algorithms. So, the creative algorithms have to be made, which would change the way a neural network works. So, for example, the researchers have found that ReLU, it performs better and it is much better than the sigmoid, which was initially proposed as a nonlinear activation function in the neural network. So we would look at some basics of the neural networks. If you are talking about binary classification, so for example, we have the two independent variables x and y, and we have some kind of label data sets, or we have, let's say, 0 and 1. These are the yellow data points that we have, and we want to separate the data set with a line, and we want to say that, okay, so on the left of the line, or the so that is our model, is a particular class, and on the right side is a another class. So we would talk about, so that is basically doing something known as binary classification. Now when somebody says that they are doing binary classification, you should focus on this word binary, because what they are meaning is that they are having two classes, with which they are trying to do classification. Now there is another class of problem which is known as multi-class classification problem. Therein you can have more than two classes. So binary classification is typically for two classes. And then a very common, like, it's so identifying cats and dogs. This is like the hello world problem now in deep learning, and there are some notations that you need to be aware of. So M is typically used for the number of samples, or for example, if you have a set of images, 100 images, out of which 60 are cats, so 60 are labeled as cats, 40 are labeled as non-cats, so 0 and 1, 1 if a cat, 0 otherwise. So M is the So M is the number of samples, or the number of training vectors, and nx is the, so you would also have the size of the input vector, the size of the output vector. So for example, in this neural network, the size of the input vector is 4, the size of the output vector is 3. So that depends upon the problem, what you're trying to do. And then we would also have, we can say that we aggregate. So we have, so x1 is the particular sample consisting of all the variables, but it is for like sample number 1. So what you can do is, for example, if you are having a 28 cross 28 image, you can stretch it over, so you can flatten it and make it as a single vector of 784 cross 1. Now you basically have a vector of size 784 for every image, so that is corresponding to x and x1. And I was talking about, if you have 100 images, so your m will go up to 100, and then these are your labels, so whether it is a 0 or it is a 1. And so you can typically use traditional Python for your computations. So we will be using TensorFlow and PyTorch, but this you must have also learned in your Python class, that NumPy, using the NumPy library, you can make the matrix operations very fast and reliable. Now coming to logistic regression. So logistic regression is an algorithm used for classification of two classes, and the simple equation of logistic regression is y is equal to wx plus b. If x is a vector, then you have to say w transpose x plus b, and then if you need the output between 0 and 1, you have to use the nonlinear activation over the linear combination. So you say sigmoid of w transpose x plus b, and sigmoid is 1 upon 1 plus e to the power of minus x. So you would, this entire number is your, so you would do 1 upon 1 plus e to the power of minus w transpose x plus b. And in some, so what you would typically do is you say if this number, if it exceeds, let's say, 0.5, then your class is 1, or you can change that threshold based upon the accuracy that you're getting. And if it is less than 0.5, you can say that it is 0. And in binary classification, y has to be between 0 and 1. And so then the logistic regression cost function. So for the cost function, so y hat is what your model has predicted, and y is what are the ground truth values, the actual values. And you would say y hat minus y square divided by 2. That would be the loss function. But he says that we won't use this notation because it leads to optimization problem, which is non-convex, means it contains local optimum points. So this is this is a problem with logistic regression. And then the function that we use, the loss function that is used for logistic regression, is minus of y hat, y log y hat. So this is the ground truth value y, this is the predicted model predicted value y hat, plus 1 minus y into log of 1 minus y hat. So this is, so you can see that y is basically, if it is 1, you will have all the if it is a cat, it will be 1. And if it has actually predicted it as a cat, then log of 1 is basically 0, right? So your loss function, it is a negative. And if it is doing, if your model is doing an accurate prediction, your loss is less. Whereas if it is goofing up somewhere, then your loss will increase. So you have to predict exactly whether it was a cat, and if it is not a cat, so there also you have to predict accurately. The model has to predict accurately. Now, so the way you would compute, so the cost function for all the samples, that will be basically you sum over this number for all the samples and divide by m, and m is your number of samples. So it says that loss function computes the error for a single training example, and it is the average of the loss functions of the entire training set. Now to basically solve for the weights, or find optimum values of the weights, the algorithm which is very popular is known as gradient descent. So gradient descent, what it is typically doing is, you are predicting the values of w and b, which are the weights, which minimizes the cost function. So you have to minimize this j and find out values of w and b. So where w is coming from is from y hat. So you can see that y hat is wx plus b. So that is where your w and b are coming from, and you have to predict, you have to basically find out those optimum values of w and b which minimize the cost function. So he says that our cost function is convex. So if you want to see the, when I used to get confused between convex and non-convex functions. So you just see the like very simply. So this is your convex function, and this is your concave function. And what he's saying is that the cost function of logistic regression is a convex function, and initially we would assign the values w and b to 0 or sometime or to some random number, and then try to improve the values for each to reach the minimum value. So in this convex function, we have to reach the minimum value. Okay, so if we reach this minimum value is for the loss in the loss function. So we would typically believe that we have reached the optimum set of parameters, or w and b in this case. And he says that in logistic regression, people would typically use 0 as the initialization rather than using random initialization. So what does gradient descent do? So gradient descent, what it does is it updates your weights, or the weights as w or b as w minus alpha. So alpha is called as the learning rate into dw. So dw is the derivative of w. So it is the derivative of the loss del of j by del of w. So it is the partial derivative of the loss cost function with respect to the weight, that particular weight. And what this basically means is that a small change in the, how much will be the change in the cost function per unit change in the weight. So if that particular weight is leading to a large change in the cost, then there would be a large change in the actual weight values, and it will be, so this change will be scaled with alpha. So alpha is the step size that we would take to minimize the cost function. Now comes the some basics on, so he discusses some basics on derivatives. So we will skip this because I am assuming that you guys are very well aware of the basics of derivatives. And so for example, if f of a is 3a, then df by df dA is equal to 3. So you would find out the derivative of this with respect to a, and then you can see the basics of calculus, and to understand more on the gradient descent algorithm, and to know how the core of your deep learning algorithm works. So at the so the bottom line is that your deep learning model is like a computational graph in which you have some inputs. For example, you have a, b, and c, and so as a particular test case, your a, b, and c, for example, has values 5, 3, and 2, and your b and c are combining to form u equal to b into c, so that is 6. And then you are saying v equal to a plus u, and so a is initial value is 5, so this is a hidden layer, for example, and then you are computing the final value. So we are saying j equal to 3 into v. So a neural network is something like a computational graph wherein you are building up on the computations that you did in the previous layers. So the derivatives in the computational graph, they would, so to compute, so as to compute del j of so del j by del a, so you would have to compute the intermediate derivatives. So for example, f of a is 3a, so del f by del a is 3, and if your j is 3v, so similarly dj by dv equal to 3. And so you would also, so it basically you what so the way you do gradient descent is something known as back propagation. So you would find out the error at the last layer, and you would back propagate that error back to the up to the first layer and update all the weights using the formula for gradient descent. Okay. And so similarly for the logistic regression, you would have a different loss function, which is y of log pi hat plus 1 minus y log of 1 minus y hat, and the whole number as negative. So yeah, he's showing a basic working unit of a gradient descent on a logistic regression problem. I will let us, yeah, so we have discussed those things, so let us, you can also go through them on your own. And so now he talks about vectorization. So deep learning shines, he says, when the data sets are big, and you should avoid loops in your in whenever you are working with Python. So NumPy provides a lot of vectorization by default, and the vectorization, whether it is done by CPU or GPU, through, so it uses the SIMD operation. So SIMD is single instruction multiple data, and so inside at the core the vectorization is done. And most of the NumPy library methods, they are the vectorized versions. So now vectorizing logistic regression, so is showing how to vectorize the logistic regression using NumPy. And yeah, so these are some things which I think belong to Python and NumPy. So we'll skip these things. And yeah, so you should be aware of Kaggle. So Kaggle is a place for data sets and competitions, and it is a very good place to learn data science on your own. And then there is a course by Peter Evil, which is on deep reinforcement learning. So this course is entirely available on YouTube. So you can go through this course, and it is basically, it will provide you with a robust understanding of what is deep reinforcement learning and why you need to do it. So starting from lecture 1 to lecture 20, yeah, so up to lecture 20. So Peter has put up all the material open source for anybody to go through. And so what are shallow neural networks? Shallow neural networks are the neural networks which are not deep. So so you just have a single hidden layer in the neural network. And then he talks about the neural network representation. So you basically have the inputs x1, x2, x3. Then so you compute the linear combination. You say W1, so this is a particular weight, W times x1, W1 times x1 plus b1. This is your linear combination, and then you can apply a nonlinear activation function to this number. It can be sigmoid or ReLU. So you say, so then that is your final output of this node of the hidden layer 1. So similarly, you will compute the other nodes of the hidden layer, and then find out the optimum values of W11, W21, W31, W41, and B11, B1, B21, B31, B41. So W is basically, so in between, so two layers, you have the matrix W. So W is represented as a 2D matrix, which has the size number of hidden neurons times nx. So nx is your input in this case. So otherwise it would have been the size of the previous layer, or the number of nodes in the previous hidden layer. And then b1 is a matrix. So corresponding to each of the input, you have a b, or to corresponding to each of the hidden nodes, you have a b, and it has a shape number of hidden neurons, comma 1. So then Z1 is the result of the equation Z1 equal to Wx plus B, and then A1 is the result of the equation A1 equal to sigmoid of Z1. Now what you would do next is you would have a W2 which corresponds to these weights, and W2 is the matrix of the second hidden layer. It has the shape of 1 comma number of hidden neurons. So 1 is the target, so you have just one hidden node, or the one output node, and you have four hidden nodes in the 4 nodes in the hidden layer. So it has got a shape of 1 comma number of hidden neurons, and you would typically do this same operation again to find out the value of this node. And so there are ways to vectorize over the different examples, and then there are different types of activation function. So one is the sigmoid activation, which is 1 upon 1 plus e to the power of minus z, where z is the input matrix. Then you have the tan h function. So tan h is basically e to the power z minus e to the power minus c divided by e to the power z plus e to the power minus c, or you can simply use it as a tan inverse of z. And it turns out that tan h works better than sigmoid function for that is the so these are some things which people have found out using by practice. And it is not like these are rules which basically are which are set, or you can. So typically what you would do is you would try different things and then come out at some conclusion, or like what activation function is performing better for your case. So then another activation function is ReLU. So ReLU is max of 0 comma z, and so if z is negative, the slope is 0. Z is positive, slope remains linear. And then you have leaky ReLU. So leaky ReLU is a modified version of ReLU, and it works as ReLU, but most people use. This was people showed that for some examples leaky ReLU performs better than ReLU. So it is max of 0.01 z comma z. So 0.01 can be a parameter of your algorithm. So you can see that you have a lot of different choices to make. So you have to decide what is the number of hidden layers, number of neurons in each hidden layer, what is the learning rate, what are the activation functions. So these are the different parameters that you would have to choose. And that is so that the if you are doing that operation, that is known as hyperparameter tuning. We will see that in the further sessions. And so why you basically need nonlinear activation functions. So if you remove the activation function from your algorithm, it typically turns into some kind of a linear regression algorithm. And so linear regression, it will whatever hidden layers you add, the activation will always be linear, like logistic regression. And you might it is so the nonlinear activation function is something which provides or adds nonlinearity to your data. Or when you're learning a nonlinear from a nonlinear data set, which is the typical property of the real world data sets. So these are the different nonlinear activation functions as we discussed. And then comes the gradient descent for neural networks. So like we have already discussed, you would compute a cost function. So you would say 1 by m is the number of examples, into you sum over the loss for all the examples. So y is the actual value, and a2 is the model predicted value. And then you would compute you would typically compute the predictions y hat. So a2 consists of your y hats. You would then compute the derivatives with respect to the different parameters, the w's and the b's, del of j by, or del of I by del w1, del of I by del v1. So that you would typically do back propagation. And then after getting the derivatives, you would update the weights. So you would say w1 equal to w1 minus learning rate into dw1. So what what is the what is the small change in w1 that would lead to, so per unit change in w1 that would lead to the change in I, or in the cost function. So after doing back propagation, you would then do a forward propagation. So one cycle of back propagation and forward propagation. So so that completes your one cycle of training. It is also known as people, if you would read the deep learning papers, they would call it an epoch. So that is an epoch of training. And then there are different methods of doing initialization to the weights. So first is the we use something known as random number initialization. So you would assign all the weights as some random numbers, and then you would have a deep L-layer neural network, which is an enhanced version of a shallow neural network, but with 3 or more layers. So basically more than one hidden layer, and the input and output layer are also considered in the calculation of the number of layers. So you would basically get your matrix dimensions right. So that is a very important thing when you are particularly building your model or architecture with TensorFlow or PyTorch. So the dimensions of your inputs and outputs and your model is something that you would check using model.summary. And so again, coming to what is it that your deep neural network is doing? So so if you pass an image recognition system, it will typically identify the edges. So the first layer is identifying the edges, the second layer is identifying the face parts, the third layer is identifying the faces, and the last output, it is identifying what exactly or which face is it, which what exactly is there in the data. And an audio recognition application, it would basically, you would input an audio or a time series, and it would identify low level sound features, and then it would identify phonemes, and then words, and then sentences. So neural researchers or deep learning or AI researchers like to think that deep neural networks think like brains. And so from simple to complex. So the initial layers, they try to identify the simple features in the data, and then the layers further in the deep neural network, they try to identify more complex features. Now, so these are the things you can see, and we have discussed on the different hyperparameters. So the main parameters are the weights, so the W's and the B's, so weights and the biases. The hyperparameters are your learning rate, number of iteration, number of hidden layers, number of hidden units, choice of activation functions. You would have to try values by your own. And what does this have to do with the brain? So this is an analogy which a lot of people criticize as well, but like I used to not believe in this, but lately seeing the performance of the language models, it is coming down to be very similar with the way the brain functions, with more data and models coming to the scene. And then there is a very interesting interview by Ian Goodfellow. So Ian Goodfellow is the guy who basically came up with the terminology of GANs, I think. Yeah. So he was the so he is the one who 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 came up with the GAN architecture. We'll be talking about GANs later. So you see, this paper has already got more than 42,000 citations, and GANs are a form of neural networks which consist of GAN neural network, which consists of two neural networks. So one is the generator, then there is discriminator. So we have seen some very brief overview of GAN in the first two classes. We will see GAN in much more detail in the lectures to come. So now we can take a 5-minute break, and then we'll come back and do a hands-on session on TensorFlow. So I completed the first week of this course today, neural networks and deep learning. I would recommend you to go to these notes, and then do spend some time with them. if you have any issues, we can discuss it in the next class. And next time we will be talking about the second week or the second course of the of this specialization. And we will break until 3, and then we'll come back and we will be doing some examples, or we will be doing the TensorFlow hands-on course. So we will break here for 5 minutes. If there is any question, I'll be happy to listen to you.
Sir,
Yeah, please.
sir, the one equation that you showed shown there, that y is equal to mx plus c, that
Mm.
m is the weight there, right? M and the c are the weight.
Yes, yes, yes.
So those weight, that is the line or the line that is moving from one node to the second node, that line is representing the weight, right?
Exactly. Yeah, the arrow. Yeah.
Yeah. So, sir, how we can say that the which node is connecting to the which node? Is it automatically getting
Yes.
connected?
So you let the model. So that's what you would train the model, and you would let the model learn on its own, and that's what. So that's about it. I mean, you don't have a control over which node is connecting to which. Typically, in traditionally you would connect all of them to each other, but then there are techniques to randomly do skip connections as well. We'll discuss about that. But typically you would connect all of them to each other and let the weights adjust such that some of them will be active and some of them won't be.
So this adjustment is according to this error, that is your.
Yes, it is
So
according to the error. Yeah.
the machine will find such that it will find such a path that where there is a minimum error, it will get connected like that.
Exactly. Yeah. So it's like you can think of it as like linear regression. So what happens in a linear regression? You don't have control over what would be the final value of M and C, right? You let the model or let the whatever cost minimization uh, do on its own, and then you iterate over different values, and then you reach a minima in the cost function, and you just typically pick those values of M and C, right? So that is what is exactly happening here.
Okay, and one more thing, sir, that if you want to calculate the m there, that is the weight, so
Hmm.
we must know the values of the x and y, right? So the input we know,
Hmm.
the output should also be known to us, right?
Yeah, so in a supervised learning problem, you would typically need to know why. So that is on like how you are framing the problem. But if it is a unsupervised learning problem, then you don't know your why. So that the different applications for different applications you would use a supervised learning algorithm. For different other applications you would use an unsupervised learning algorithm. But if we are using a supervised learning algorithm, you would definitely need to know the x and y, and this is known as the labeled data set. So you have labeled your x's with y's.
Okay, and sir, one more thing, that when the training is completed, after the completion of the training, the weights, that is yum value get fixed, right? After the training.
Mm, what do you mean by M value get fixed?
M means that we are training those networks. So after training that network, the M value that means that those weights get means we are getting those weights now after training.
Yeah. You are getting the weights. Yeah, exactly. You are getting the weights after training. I mean, I didn't understand what you are trying to say.
Like sir, y is equal to mx plus c, right? So y we
Hmm.
know, x we know, right?
Yeah,
So unknown
yeah.
is there m. So
M and C.
m and c, right? So if we
Yes,
want to find the m and c, we must know the y and x. So
exactly.
yeah, so output we if we know the output and if we don't know the input, these two
Yeah.
conditions can be known only during the training.
Yes.
So after the training
So you,
we will get
hmm,
those m and c values, and
yes.
uh, when we have to test that model, we are using those same m and c values, right? But at that time
Hmm.
y is unknown to us.
Yes. Yeah.
Okay. And one more thing, sir, is this
No,
network
no, no.
entire?
So why is not unknown to you? I'm sorry. Why is not unknown to you? Why is known? Like you know why. You know the ground truth.
uh, yes sir, but during the test phase, when we are testing that model.
During the test phase, you don't know why. You let the
Huh.
model predict you do your why predictions. Yeah, during a test phase, you would typically not know why, but then you know it, right? So you would compute the error in the test case
Okay, so
during
this
testing.
so this entire network is working only on a can we say on a single equation y is equal to mx plus c?
I mean, very simplistically, yes.
Okay, so as the network gets deeper and deeper, so is that getting is that equation getting more non-linear also?
Exactly. Yeah. So that equation, see, there are, so you would have to see your see the way they frame the deep neural network. Okay. So that equation is becoming more and more complex. So you would have your input layer, you would have your hidden layer. So you would compute for each node of the hidden layer, you would compute this linear combination. So y is equal to mx, so mx plus c is your linear combination, and then you would apply a non-linear activation to it. So you would do the same for all the nodes of the first hidden layer, and then again for the next hidden layer you would do a linear combination applied to the non-linear activations that were computed in the previous hidden layer. So then you would do the linear combination, and then you would apply a non-linear activation. So your equation will become very complex. I mean, it won't remain y is equal to mx plus c, but it is a very highly evolved form of y is equal to mx plus c.
Okay, so can we say it is just like y is equal to m1 x1 plus m2 x2 like that means many
I mean,
number of.
see, very simple. You can just say is y is equal to f of x. Now this f, what it is depends upon your architecture. It depends upon lots of different things. What is the activation function you are using? What are the how many deep layers you are using? So that depends upon a lot of factors.
Okay, so when we
Okay.
design okay sir, so when we design this network sir, those number of nodes increasing or decreasing, is it on our in our hand that
Yes. Yes.
okay, okay,
Okay.
yes sir.
Yeah. So okay. Yeah. You have anybody else has any question? No question. Is everybody understanding everything or nothing? Either either of the things is true, I think, if there are no questions. Okay. Yeah, so we'll start with TensorFlow quick start for beginners today. And this short introduction, so they say so there tutorial it says it uses Keras. So Keras is a wrapper over TensorFlow, and it will minimize a lot of the code. So if you guys remember from our last class, we had seen an image classification from scratch example in TensorFlow or in Keras, which is a part of TensorFlow now from TensorFlow version 2. So you can see that. So you can print the TensorFlow version, and what we do is, so TensorFlow comes with this Mnist data. So Mnist is a classification data set. So it's a labeled data set. So you have your x and y's in your Mnist data set, and yeah, so we can see, yeah, from this. So Mnist is a data set of handwritten digits, and it is prepared by Jan LeCun, and you basically have images of the numbers from 0 to 1, and they are labeled as, so the label is, so the label to the image with number 0 is 0, label with image having number as 1 is 1. So those are the labels that you have. And see, this is the paper 1998, Jan LeCun. This was the first paper that talked about this kind of a thing, convolution neural networks. And okay, yeah, so these are the for example, these are the images that you have. These are x, all of them are your x's. And so you can see 1 2 3 4 5 6 7 8 9 10. So you have 100 examples, so 100 labeled data sets with x and y defined. And so you see, you would typically, in this problem, you would want to give the image to your model, and you would like to predict what number it is. So that's about the Mnist, and this is something we will run here. So Mnist comes as a, so it's become a hello world type problem for machine learning these days. And you can see, so you should always check the shape of your matrix. So let us see y train and x train and y train, how do they look. So you see, you have 60,000 samples, 60,000 examples, and you have 60,000 images of size 28 cross 28. So the first label is 5, second label is 0. So you have 60,000 labels, and the labels are integers from 0 to 9. And now we are building a machine learning model. So we will use a specific version or class of model from Keras. It is known as the sequential. So there are two types of ways in which you can build a model. One is sequential, another is functional. So we will see functional later when we go through GANs. So in sequential, what we are doing is, so we are inputting an image. So you are building up, so you're saying model equal to tf.keras. So you use Keras from the TensorFlow dot models. So there is a models class inside Keras, and then from there you use the sequential class. So see, this will return you a model object. So this one, whatever you give inside are the layers in the model. So the first layer is a so the layers you use from the layers class in tf.keras. So the first one that we use is called flatten. So you would flatten this 28 cross 28 input. So you would have to give an input shape here. So your input data, it will come and it will feed into the model. First, it will get flattened. So you would have a 784 cross 1 input. Then your first layer is tf.keras.layers.dense. So your first layer is having 128 neurons. The activation function that we are using is relu. And then what we are saying is you give a dropout of 0.2. So we have not discussed dropout today, but dropout basically means that you randomly switch off 20% of the connections in this case. So you can give the number, a number as an argument of the dropout function here from 0 to 1. And whatever, if you give 0.5, 50% of the node of the connections will be switched off. So that is so a dropout is basically used to enhance the performance of your model. And then you are basically using another layer. So you are saying tf.keras.layers.dense. So this will, so the output, this is the final layer, the final output. So we have, the output should be so we have 10 numbers. So what we will do is we will vectorize, or we will create. So from our labels, so from 0 to 9, we will make them into a vector of size 10, which will be so if it is 1, so for example, so you have numbers from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Now what people have found out is that to be able to better, yeah, we will make this into we'll make this into a text. And delete this one. So what people have seen is that not working. Yeah. So 0, you will basically be 1, then 0, 0, 0, 0, 0, 4, 5, 6, 7, 8, 9, 10. So 0 will be a vector which is 1, 1, 0, 0, 0, and like all numbers as zeros. So 1 will be 0, 1, 0, 0, 0, 0, 0, 0, 0, 0. So similarly, your 9 will be 0, 0, 0, 0, 0, 5, 6, 7, 8, 9, 10. So this will be your 9. So what we would typically do is in the output layer, we need in this problem. So you see the way we define our model is depending upon the problem. So we need 9 nodes in the output. So we say tf.keras.layers.dense 10, or sorry, not 9, 10. Okay. So then what we would do is we would say that, okay, so predictions, if you want to predict from the model, so predictions will be model x train colon comma 1. So this will give just one sample to the model, and it is giving us some kind of predictions. And now these predictions you would apply softmax function. So softmax will turn these, so you can see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, so these are the 10 numbers. So these are the numbers you are getting from your model, and softmax will basically turn these numbers into probabilities. So you can see that the probabilities of the first number being a 0 is 0.12, being a 1 is 0.07, being a 2 is 0.08. So we can see that the highest probability is for it being number 0, I think. Yeah, so then our model will classify it as a 0. And so you can also use the softmax as a part of your model. So you can say tf.keras tf.neural network nn.softmax. You can include it in the model as well, and you can define the loss function using as a sparse categorical cross entropy. So this is a specific loss function which is very useful for classification problems. And so this is the loss function we are defining from tf.keras.losses class. And then you can see a typical loss. So we have not trained the model, but with some default initialization, we can do the predictions, we can compute the losses. And before you actually train the model, you would do something known as compilation. So in compilation, you define the optimizer. So what is an optimizer? We will discuss these things in detail in the theory sessions. So the optimizer that we are using here is Adam, and the loss function is loss underscore fn that we defined here. So we have to define the loss function, and we have to define a matrix. So matrix is some evaluation matrix on which you would want to see how your model is performing. Now to train the model, so you see your x train and y train were here. Okay, so these are x train is 60,000 comma 28 comma 28, and y train is 60,000. So you are having for each image 28 by 28 image, you have a label. The model is basically first doing flattening, then it's creating one hidden layer, and then dropout, and then the output. So we will train the model using the function model.fit, and we are training it for 5 epochs. So 5 times over all the examples or over all the samples. So you can see that. So we are tracking the accuracy, but the model is being trained on the loss. So it is being optimized on the loss function. The loss function loss values are decreasing. The accuracy is increasing. Accuracy here basically means how many percentage of the samples you were able to accurately predict as as right. So if out of 100, 98 are predicted correct, so the accuracy becomes 98%. Now you can do run model.evaluate on the test data set. So this will basically give you the loss and the accuracy on the data that the model has not seen. So that is what model.evaluate does. And then if you want to return a probability, so this model will typically return you some values, some numbers. So a vector of 10 numbers. If you want to return the actual probabilities, so this is a probability model where you are having, so you are concatenating the model and the sequential, and the in a sequential form you are adding the softmax layer to it. So this is our probability model. And then you can see that for the first 5 test data sets we have run the probability model, and these are the different probabilities. So this is for the first example. So you can see that the probability is highest for the number 0, 1, 2, 3, 4, 5, 6, 7. So this is classifying. So this is 0.99, and so this is classifying this as a as the number 7. So is there any question in this example that you would like to ask? No question. Am I audible?
Yes, sir.
Yes, sir.
Okay. So then, yeah, the next example that we would see is a basic classification example. So in this case, we would build a simple classification model. So you classify the images of clothing. So what kind of clothing it is, and so what you would typically do is you would import the libraries, and we would use the fashion Mnist dataset for this case. So fashion Mnist is an evolved form of Mnist. So Mnist is for the digits, like the numbers, recognizing the digits. Fashion Mnist is whether it is the image is a shoe or a purse or a shirt. So this is the fashion Mnist data set, and there is a very nice tool to visualize this. Yeah, we'll see these things later. But okay, so fashion Mnist basically contains 70,000 grayscale images in 10 categories, and it is slightly more difficult than the Mnist dataset or the Mnist problem. So it is also available as a inside TensorFlow, and you can see that so these are the labels 0, 1, 2 up to 9, and the classes corresponding to each of the labels, and then you have the class names. So these are the names of the class. So we will first do some kind of data exploration. So there are total 70,000 images, but train images have only 60,000 examples or samples. And then the length of the train, so that we have the labels as well. So each label is an integer from between number 0 to 9. And so you can see that these are our labels. So train labels, and we have the test labels, test images, and then we have the test labels. So since this is an image data set, it must be pre-processed, and you should so the values are from 0 to 255. So you should note this. For our case, we should bring the data in the range 0 to 1 or -1 to 1. So you can see that this is looking like a shoe, and the values are from 0 to 255, and they're scaling the values to the range to a range of 0 to 1 before feeding it to a neural network model. And so you basically scale these images, and then we would plot some scaled images. So you can see that with the labels. So you can see that the scaled images with the labels look like this, and then we will build a model. So similar to the previous example, we would we would use a flattened layer first, and then a dense layer, and then another dense layer. So the hidden dense layer will have the number of neurons as 128, and the activation function that we would use is relu, and the final output is a dense layer with 10 with the number of nodes as 10. And then yeah, so you see the first layer. So we flatten 28 by 28 to 784 pixels, and then we compile the model. So we say tf.keras.losses.sparse categorical cross entropy from logits equal to true. So this will basically do is it will make your labels into some form of vectors. So this will do it in an automated way. So you can see that. So after doing all of that, so what are your train images? And then you have your train labels. So you have these numbers like this, and then the you are saying model.fit train images comma train labels. So this loss is taking care of the losses. So keras.losses dot sparse cross entropy. So we will see this in TensorFlow. Yeah. So it says that this computes the cross entropy loss between the labels and the predictions. So if the y true is, so it says use this cross entropy loss function when there are two or more label classes. We expect the labels to be provided as integers. If you want to provide labels as one hot representation, so that representation that I was showing in the previous collab notebook, this one, this is known as one hot encoding or one hot representation. So what they're doing is inside this sparse categorical cross entropy class, they are first making your integer into a one hot encoding. So they provide us with this feature that we can either provide labels using one hot representation. So if we are doing that, we would have to use categorical cross entropy. And if we are directly giving the numbers, let's say 1 or 2, then we have to use sparse categorical cross entropy. Okay, so there should be number of classes, floating point per feature for y pred and a single floating point value for y true. So the standalone usage is, so for example, your y true is 1 comma 2, your y pred is 0.05, 0.950, and so these are the numbers which are generated by your model. So so then the keras tf.keras sparse categorical cross entropy, this will then try to find out the loss between y true and y pred. So yeah, so we were here, and so we would train this model for 10 epochs. So you can see that, yeah, so this number 1875 is basically, are they giving any batch size? So we have to give a hyperparameter known as batch size, or if we don't give, it will take on its own the batch size, default batch size they will take. And batch size is basically, it is so for each, within each epoch, the number of times the training happens is equal to the number of samples divided by the batch size. So it happens like 1875 times. So one out of this 1875, in one iteration, it will take like m samples, and that m we call as the batch size. So you can see that the loss is decreased, the accuracy has increased, but the accuracy this time is not as high as the Mnist, but this is just for 10 epochs. So you can see that it is slightly challenging as compared to the Mnist problem. And then you can also have the probability model. You can add the softmax layer and do the predictions. First image, that is estimating as the last class. So the last class is an ankle boot. So that's what it is doing. And yeah, so these are like some applications of this model. Like you made the model, now you run this model, plot the images. We'll go to the next example. So it is load CSV data set. So this example shows you how to load your generic CSV dataset from the disk and pre-process it into a form suitable for training. So it will focuses on loading, give some examples of pre-processing. So you first load the libraries, and then you read pandas data frame. So this is a pandas data frame. This is a tabular data with the variables such as length, diameter, height. So these are the different variables, and it says this data set contains a set of measurements of app alone, a type of sea snail. So this is a measurement of this thing, app alone. And yeah, so you would basically, okay, so the nominal task for this data set is to predict the age from other measurements. So separate the features and labels for training. So you see here in this data set, we have the features as length, diameter, height, weight, shuck weight, and viscera weight, shell weight. And what we have to predict is the age of the sea snail. And so we would copy the features in this data frame abalone underscore features, and then in the labels what we would do is we would delete age. So we would say dot pop age. So we would treat all the features identically in this example and pack all of them into a single numpy array. So we would typically say np.array abalone underscore features. So then the yeah, so then the model, in the model we would have a dense layer, so a hidden layer with 64 nodes, and a output layer with 1 node. We would compile the model using the mean squared error loss, and the optimizer that we would use is Adam optimizer. And so here, like this is 1 2 3 4 5 6 7 8. Okay, so we have 8 inputs, and 1 2 3. Okay, what is the shape of this? Okay, yeah, it is 7. So it says that from the features they have removed age and app alone dot labels. Yeah, so the labels that we have, so these are the labels which are actual numbers from 0 to 3320, and the shape is 3320 again here. Okay, so then what we would do is we would train this model. We would give the features as the input, the labels as target, and we can see that the loss started decreasing. And you have seen the most basic way to train a model using a CSV dataset. Next, you will learn how to apply pre-processing using normalized numeric columns. So in the basic pre-processing, so in this case, you see, we have not pre-processed the age. So although the features are within the range 0 to 1, but age is not. So we would create an object of the class normalization from the layers tf.keras.layers, and then we would use normalization.adapt method to adapt normalization layer to your data, and only use your training data to adapt a pre-processing layer. So as I was discussing before, you normalize only using your training data set, and the normalization that happens to validation and test data set, that is basically using the data from the training. So we would say normalize.adapt able on features, then use normalization layer in your model. So we say yeah, so we say normalize comma layer dot dense, then okay. So we would run this for 10 epochs, and then we would okay. So this was about a very simple CSV example, and then we have the mixed data types. So you must have heard of the Titanic data set. So you would have to predict. You have the different inputs, and you have to predict whether the person drowned or not on Titanic. And nominal task is to predict who survived. So you would typically read the Titanic dataset like this. So you see survived, this is the target that you have to predict, and you have the different features. So you would, yeah, so you what you would do is you would extract the features and the labels from the data set, and because of the different data types and ranges, so you can see that here we have the data as third first, and then the different types of decks, the embarked town. So you can't simply stack features into a numpy array and pass it to keras.sequential, and each column needs to be handled individually. So as an option, you could pre-process your data offline to convert the categorical columns into numeric columns, and then pass the processed output to your TensorFlow model. The disadvantage to that approach is that if you save and export your model, the pre-processing is not saved with it. The Keras pre-processing layers avoid this problem because they're a part of the model. So in this example, you will build the model, a model that implements the pre-processing logic using Keras functional API. So here now you see we are using the functional API, and there is a sequential API for Keras, and then there is a functional API. So you can read more about the functional API on this page. It's a way to create models that are more flexible than the Keras sequential API. And functional API can handle models with nonlinear topology. So if you want layer 1 to connect to layer 3, it is not possible in the sequential API because that would make your architecture only in a sequential manner. So if you want a customized architecture, shared layers, multiple inputs, outputs, so you would have to use the Keras functional API. And the main idea is that deep learning model is usually a directed acyclic graph DAG of layers. So the functional API is a way to build a graph of layers. So you can read more about the functional API. They have a lot of material on this. Coming back to our example, so the functional API operates on symbolic tensors. Normal eager tensors have a value. In contrast, these symbolic tensors do not. Instead, they keep a track of which operators are run on them and build representation of the calculation that you can run later. So here they are giving an example of that. So for example, you take an input class, you create an input object. So you create an object named input with the small I, and which is an object of the class input with a capital I, and then you just do something. You say 2 into input plus 1 is your result, and then you are just printing that result, which, yeah, so you're not giving anything, and it is not having any value. So then you can say that you can say tf.keras.model. So this is how you would build a model. So what are your inputs? Input is this input, and output is the result. So then you would pass the number 1 and 2 to this. So you can see that this prints 2 into 1 plus 1 3, and this prints 2 into 2 plus 1 5. And then to build the pre-processing model, you start by building a set of symbolic keras.input objects matching the name and data type of the CSV column. So for name, column in Titanic features dot items, so you say data type equal to column dot d type. So that would yeah, I think if this is, I will print this again so that it becomes more clear. So what we are doing is we are looping across all the items in Titanic dot features. So we are saying d type equal to, so what is the data type of that particular column, and if d type equal to object, so you convert, if it is an object you say make it a string, otherwise you make it a TensorFlow float. And then the inputs is an empty dictionary here. So in that you would keep filling your values. So you convert your object to string or otherwise into float, and then you say that so the name, so it will, so the name will come in. Okay, we will also use a print here, print name comma column, so that it is more clear. So you can see that first it is printing the name of the column, and then it is printing the entire column. So this is the column named sex, and it is printing the entire column. So the first is male, female, and the last one is also male. And then so this basically loops along all the columns, and if the data type of the column, so it tries to identify the okay, so we will print the d type as well. So you can see that, okay, so you can see that it is printing name is this one, then the column is to here, and then it is printing the d type. So the data type is an object, so if it says if it's an object you make it a string, and then in the dictionary you have the name, you have a key value pair. So the key is a string which is sex, and the values are these values. So these are the values which are provided as keras dot input, and then we are printing the input. So you can see what we get, what we finally get is basically a dictionary with the keys as strings and the values as keras tensors, with their respective shapes and d types, and created by that particular layer. Now the first step in your pre-processing logic is to concatenate the numeric inputs together and run them through a normalization layer. So what are your numeric inputs? So your numeric inputs are name, so in name colon input for name comma input in input dot item. So you would basically extract all the numeric inputs. So if the data type is float, so then you would basically extract them into this numeric inputs, and you would say layers dot concatenate. So you would basically concatenate them, and you would say dot values, so you would convert it into the matrix, and then you would extract this layers dot normalization. So layers from the normalization class of TensorFlow, and adapt. So you would run norm dot adapt to this numeric inputs, and then you would say all numeric inputs equal to norm of x. So you can see what are our numeric inputs. So we have 4 numeric inputs here, and which are created by the layer normalization. So then we collect them into, so to concatenate them later. And then for the string inputs, you use tf.keras.layers string lookup function to map from strings to integer indices in a vocabulary. And next we would use the tf.keras.layers category encoding. So this is just like one hot encoding wherein numbers from 0 to 10, 0 to 9, they are being encoded into vectors of size 10. We are doing category encoding. So for example, category encoding, what it would do is, for example, in this case class, you would have three strings like first, second, and third. So this will have 3 categories. So it will do category encoding and call it as 0, 0, 1, 1, 0, 0, or 0, 1, 0. So that is what is meant by category encoding layer, to create a one hot vector for each input. A layers dot embedding would also work. So you can check the pre-processing layers guide and tutorial on more on this. And so we would run this, and I see it is already 3:45. So I would suggest that you run this, and this is very long. So you run this at your end, and if you face any issues, we will start from here in the next class. And what I was not able to do, I think, was TensorFlow Quick Start for experts. This will be faster. Okay, so that was all about today's class. And if you have any questions, I can see. Okay. Yeah, so the link of the notebook is on TensorFlow tutorial page. I will also share the link in the presentation, which is the same presentation in which I am updating for all the classes. And yeah, so we will stop.